So you said for you grade Sundays or do you grade Saturday nights as well?
Probably Sunday night.
Okay, so as long as we get the lab in sometime,
Sure.
yeah. All right, thank you. And do we have to do anything turn in special to turn it in if it's late then, or just turn it in?
Well, if you're locked out, just email it to me.
Yes, sir.
Okay, I'll go through this list and then we'll go back and let people record. Let's see, were you guys able to pick up your kits? Let's see, Lonnie, you have a kit. I mailed some components. Hopefully you received those. You're gonna make me look at the chat, huh? Okay, Martin got his, good. Okay.
For Mustafa and Edgardo Bellin, we got ours.
Okay, good. So actually, I'm just gonna put just notes. I'll clean this up later. Okay. Martin got his. And then here, Mustafa, right? You got your.
Yeah. Yep.
And Eduardo.
Yes, sir.
Yeah.
Okay, let's see. Amir and Muiz, did you get yours?
Yeah, well, we got the kit.
Okay, good. And let's see. I don't have an assignment for Randall. Randall, are you on the line?
Yeah, I'm here.
Okay. What were we doing with the kid here? This might be an old, I thought I had one assigned to you.
Yeah, I think you had maybe, I don't remember exactly who, but Din, maybe, I don't know.
Do you have a kit or do you have a way to do the lab?
Yeah.
You do?
Yeah, I do have a kit. Yeah.
Oh, I'm not sure if I understood. Do you or do you not have a kit?
I do.
Oh, okay, good. Okay. And I don't think I assigned a partner then. Din has not shown up. I don't even know if he's still in the class.
Yeah.
Din, are you on?
What?
I didn't understand that. Din, are you on the line? Okay. These are okay. This is okay. We got partners here. So Randall, I guess you're operating alone, right?
Yeah.
Okay. And then Joshua. Okay, let's see. Okay, this may be an older list. Ruben, are you on?
Yeah, I'm on.
Do you have access to a kit?
Yeah.
Oh, are you partnering with somebody?
I believe you partnered me with Joshua.
Okay, and then Joshua was up here. And so do you have the kit, Ruben, or does Joshua?
I have the kit.
Okay, good. I think this is an old list I'm looking at. I didn't download the latest one. Okay, we're okay here. And Christian, let's see. You and Jonathan. Jonathan has a kit, right?
Yeah,
We have the kit.
Okay, good. So I think we're covered. The only one that's missing, I don't think he's attended any of the sessions, is Din. Okay, let's move on to our lab. I'll go back here and just do a quick review. Who needs to record that hasn't had access yet? Okay, I can allow Christian to record. Speak up if I missed you. Come on. Allow to record. Actually, all the ones with the dot are recording. Okay. So most of you are recording. Jonathan, you have permission. Okay, I think we're good to start. So I'll talk a little bit about our lab and then I'll talk about the analog discovery. Let's see, where's our lab right up? This should be somewhat review. We built op amps in the 117 classes. So this shouldn't be totally foreign. The you see the lab right up, correct?
Yeah.
Okay. Yeah, so just some properties of an op amp. When this node, when it's in its operating range, the voltage at this node and this node will essentially be the same. These are called like the summing points. An op amp will have very high impedance, but like for instance here, if I tell you this node to ground, this node gets pulled to ground. And then they generally have relatively low output impedances. Internally, they have a very high gain bandwidth gain, and we'll look at the gain bandwidth curve again. But we use feedback to control that and get an operating range that is useful for our designs. So we went over some of that. We went over the pre-lab last week. We did SPICE simulations. So we got 9 steps to the to build these. And so what we're going to do is we're going to build the inverting, non-inverting, the inverting amplifier, and then we're going to build this differential amplifier, which is essentially a combination of an inverting amplifier and a non-inverting, but you have a differential input. And I'll talk a little bit about more about that in a moment. And then we're going to hook this circuit, these back-to-back diodes, to the input of that amplifier. So this circuit here, this just kind of represents a condition where you would use a differential amplifier. If I stick my scope probe here, I'll just see the signal that's coming in. And if I stuck a scope probe here with a reference to ground, I would just see basically the ground. So we use the differential amplifier to see what's actually going on across those diodes. And actually that circuit, these two opposing diodes, that's very common. Just about any integrated circuit that you have these days, the first thing that happens at the pin, especially if there's like a differential signal coming in, is you'll have 2 diodes like that back to back. And what they do is they basically clamp the voltage. So like, for instance, modern integrated circuits, like they'll have IOs at like 5 volts or 3.3 volts and so forth. But the core processors, like on a microprocessor, they're operating at like plus or minus 1 volt. So they have some voltage converters inside the integrated circuit. But the thing is, the little transistors in there are all very sensitive to voltage levels that can break down if the voltage exceed. And then there's also the issue of like, if you touch these things and you have static electricity, or there's a voltage surge on the power line or the signal or something like that, you can blow out the whole internal circuitry. So what these diodes do is they clamp the voltages to a specific level. So a diode will have like a PN junction in it with the junction will turn on at let's see, we actually did a simulation of this, I think a week ago or 2 weeks ago. It'll turn on at like 0.6 volts or 0.5 volts. And so with this circuit here, it'll basically clamp the amplitudes to plus and minus 0.6 volts. or we'll see when we actually go build and test it. Okay, so that's what's going on there. And then I had some notes. Let's go back and review those. So this was the pre-lab calculation. So our gain ratios for the inverting amplifier is 1 plus RB divided by RA. So we're going to build an amplifier with a 3 ohm. I'm sorry, a gain of 3. And then we're going to build a non-inverting amplifier with a gain of 2. So we'll essentially use the same resistors. The circuit I built earlier today has a 2K ohm resistor in the feedback and a 1K ohm to ground. So I have a gain of 3. And then in this case, I use the same 2K and 1K. I'm going to turn on the lights too for a moment. Hold on. Okay. And then later on, we'll do the differential amplifier. And in that one, we use all 4.7K or something similar to that. We'll use all the same values for that one. Okay, so just some review. On the output of the amplifier, you can't get all the way to the supply voltages. So like if we have the circuit and we're trying to drive it all the way up to 10 volts, it will stop. In the SPICE simulations, it stopped around 9.8 volts. What we're going to see today is it'll stop at a level lower than that. And then in the negative direction, we'll see that it stops. I think last time I built this, I think it was like around 2 volts. So like if we're trying to drive down to minus, I keep saying minus 10. Actually, with the analog discovery, we're going to be using plus 5 volts and minus 5 volts. So we'll probably be able to drive up to like positive 4 volts at the output and maybe minus 3.5, 3.8 volts at the negative swing. But anyway, it's this internal circuitry that controls the current flowing through the amplifier and biases it and provides a load and so forth that prevents us from getting to the full supply voltage levels. Okay, just another review. One thing we'll be doing in this lab is testing the gain. The way we do it in the lab, I don't particularly find it useful, but anyway, that's the way Professor Headley set it up. So we'll just continue and do it his way. But you know, generally what I would do to figure out what the bandwidth is of an op amp is I would set the gain to 1. So I'd have like the same resistor in the inverting feedback and then input. I'd set the gain to 1, and then I'd basically just increase the frequency to where that gain started to diminish, and that'll tell you where the full amplitude is. And then, you know, you can do the other things like you can then like set the gain to 10 and then set the gain to 100 and basically create this line and figure out where this corner is. But generally, they have very high internal gain. This is like 10 to the 5th. So I'd be like over 100,000. But they start rolling off like around 100 hertz. Okay, so that's that. In your analog discovery kits, the lab is written around using the old op amp, the LM741, and it's still in use today. I mean, it's great for audio ranges. So I mean, we can only hear up to like 20 kilohertz, and so it's more than useful for that. It probably maxes out like its unity gain is probably somewhere like around 80 kilohertz. But for sensors and audio projects, it's fine for that. The one in the analog discovery kit is a much more sophisticated. It probably was designed like within the last 20 years, whereas the other one was probably 40 years ago or 50. But this device has much broader bandwidth. So some of the things we're going to be checking, like the offset voltage, in the analog discovery, it may be plus or minus 3 millivolts. In the OP37, or also in your kits, you have OP27s. It may be in the range of like microvolts. And so we have actually some specs here, so we can look at that. So like, for instance, here, this is the OP37. So they specify the input offset volt voltage at typical, this version here, like this version, there's 3 versions apparently. 10 microvolts, typical 20 microvolts, 30 microvolts. So with those devices, you may not even be able to see much of a offset voltage. Okay, and just some other things on the specs. Input resistance internal. So this one, that says it's got like a 4 mega ohm. Here, this one's got 6 mega ohms of internal resistance. So again, that's that input resistance between the plus and minus terminals. It's generally rather high. For common mode signals, it's a little bit lower. Common mode rejection ratio. So what this is saying, that if you have a common mode signal, it's going to attenuate it, like this one here, it says 120. So that's and that's in dB. So that would be 10 to the 6. Yeah, 10 to the 6 for every 10 dB represents a gain of 10. I'm sorry. Let me do that. I got to punch that out of my calculator. I forget it in my head. Let's see. If I have 20 divided by 20 equals 1, and then I take the inverse log equals, oh, I'm doing that wrong. Let me do this. 10 log times 20. Okay, 20 dB. I'm sorry for the confusion. But anyway, 20 dB corresponds to a gain of 10. So 120 dB corresponds to a gain of 1,000,000, I believe. Let me actually just do that. 120 divided by 20 equals 6. Shift log 1, 2, 3, 1, 2, 3, 4. Yeah, 1,000,000. Okay. So if you have a common mode signal come in, it should be attenuated. So attenuated means diminished by a factor of 1,000,000, ideally, with this device. I mean, there's other effects that happen, like noise and things that can corrupt that. But anyway, it should attenuate quite a bit. So these devices are designed to provide gain, which would be amplification, to a differential signal, but attenuate common mode. Okay, so here's the gain curve, and then we're going over the specs. What else do we have? Gain bandwidth product. On this device, it's rather high. It's like, oh gosh, 63 megahertz. I don't have the spec for the 741, but it's probably less than half of that. This is a much better device. It's a much more modern device. Okay, just talking a little bit about common mode signals. So I'm very familiar with them because I've designed many circuits that attenuate common mode signals, that are try to get them out of communication systems. So this is if you have like an Ethernet cable, USB cable, this here is a picture of an Ethernet cable. We transmit differentially. And so when this cable's positive, this one's negative. When this one's negative, this one's positive. So we don't transmit with a reference to ground. We transmit the signals differentially balanced on the 2 wires. And so the reason is when this arrow here is the current. And so the right-hand rule, if you remember from physics, you point your thumb towards the direction of the current and your fingers curl in the direction of the electromagnetic field. And so when you have them opposing, the fields cancel each other. Whereas if there's a common mode signal and they're both going in the same direction, the fields compound with each other and then create noise that'll fuzz up a TV or radio or whatever. So when we design like a communication system, we want an amplifier that will attenuate any common mode and put very little common mode signal out on the line. Because that'll radiate noise when you're transmitting your data. But if there's something happening nearby, maybe a motor running or something that's creating a lot of electromagnetic noise, it'll stimulate both of these cables simultaneously, and then it'll create common mode currents. So additionally, at the receiver, we want the amplifier to reject common mode signals coming in and only pass the differential signals. So that's why the common mode rejection is important. So in this lab, we're going to build this differential amplifier, and the gain is set by the ratio of these resistors. So like if I want a gain of 10, I'd make this resistor 10x of that one, and this resistor 10x of this one. Today, we're just going to use them all the same values. We're going to use all 4.7K or something similar to that. Whatever you have in your kit that you can find, you can just use all the same resistors. So our circuit will essentially have a unity gain. Now to test the differential gain, you can send the signal in one side and then ground the other, or vice versa. You can send the signal in here and ground this side. And then if you do that, if you send the signal in here, the signal coming out will be in phase. If you send the signal in here, the signal coming out will be differential. I'm not differential, I'm sorry, out of phase by 180 degrees. Because again, this is essentially a combination of an inverting and non-inverting amplifier. And again, it's useful for communication circuits or instrumentation. A lot of times instrumentation will have a signal output that doesn't have a ground reference. And so you'll send it into something here. So when you don't have a ground reference, or you have a floating ground reference or something like that, that's when you would use a differential amplifier. Now to test the common mode gain, we essentially tie the two inputs together and launch the same signal into both of them. And again, if we have like a 1 volt peak to peak here, we should have something in the millivolts out here. It should be much lower. Okay, I don't know how many of you have experience with the analog discoveries. They're actually pretty cool. I find them quite useful because like a lot of times I've got a bench of equipment here in my lab with oscilloscopes and signal generators and stuff. But I just find it often useful to just hook it up with the analog discovery because it's easier to just cut and paste my displays to show performance. So it's actually very convenient. I'm not ready to remove all, I've got my bench is all crowded and cluttered. I'm not ready to take all that stuff and sell it yet, but I do find the analog discovery rather useful. So this is the pinout that we'll use. So this is very key to hooking up your circuit. We've got oscilloscope channels. And so I always make a point to hook up the negative to ground, the negative scope channels to ground, and then the positives go to my circuit. And then here we have ground, and then the plus voltage, and then the minus voltage. So those are referenced to these ground pins. And then we have a waveform generator 1, and then a waveform generator 2. Today, we're just going to be using waveform generator 1. And then we got 2 grounds, and then we have all these digital signals, which we really won't be using in this class. Okay, and then the rest are just pictures. I can come back to these later and refer to them, but I'll open up the WaveGen program. So the WaveGen is a program you can download from the Digilent website. So the Digilent is the people who make the analog discovery. So you can just Google that and Google waveforms, Digilent or something like that, and they'll take you to their website. And then if you look in the search bars, there'll be like software, and you can find the download for that. So that's what you use to run it. So I'm going to back up. After you've loaded the software and you plug in your analog discovery to the USB port of your laptop or computer, you'll get a picture like this. And then what you can do is you can click on scope. So we got the scope, and then you can click on the WaveGen, and that'll open up. And here, what you see for this non-inverting amplifier that I have running right now, I set the amplitude to 500 millivolts. So this amplitude is peak. So what I'm going to get in my display is 1 volt peak to peak. So yeah, just remember that. I mean, it'll be obvious when you test that this is just peak, and you can get peak to peak. But you have the opportunity here to change the frequencies and the period, if it's like a square wave, and the offsets and symmetry and things like that. So like if you have like a square wave and you want it to be asymmetric, you can change that. You can control the phase. So there's a lot of capability there. And then if you want to use the second one, let's see. Oh, here it is. You can turn on channel 2 here. Okay, the other things are the power supply. So a lot of times in these labs, I've taught this over Zoom before, and in many cases I've marked them up. I don't think I've marked up this one. I think in your lab it's going to say plus or minus 10 volts for the power supplies for the op amp. The analog discovery will only put out +5 and -5. So wherever you see plus or minus 10 volts DC for powering your op amp, use plus or -5. And you have the control here again. You can control these 3 volts or 1 volt. These are DC references that you have access to. And then you always have to remember after you set those that you can turn them on and off. So like here, I'll just turn it off and look at this scope. So my output flatlined. So I go back in here and I turn this on, and then here's my output again. And then so we went over wave gen and stuff. I'll back up and just look. So the first circuit I built is these are all inverting. I guess I don't have a picture of the non-inverting amplifier. Yeah, these are all the inverting. Oh no, here it is. Okay, so basically here's my op amp. Here's pin 1 is the side with the dimple. We don't use pin 1 and 5. I mean, they have a purpose, but we're not going to use it in the lab. Pin 1 and 5, you can put like a potentiometer and tune out the offset voltage with that, but we don't need to use that for our lab today. But anyway, I basically have a feedback resistor. In my case today, I've got 2 k ohms there. And then we've got a resistor going to ground. This is, again, the non-inverting. And then the signal comes in, that's the yellow one here, comes into pin 3. And I've got the orange channel 1 oscilloscope probe on pin 3. And then I've got the minus supply set at 5 volts on pin 5. I'm sorry, pin 4. Pin 5 is not used. Pin 6 is the output. So that's where my resistor is going. Again, 2 to 6. I've got the second oscilloscope, the blue wire there. And then I've got my +5 power on pin 7. Okay, so that's the circuit I have hooked up. And then here's the wave gen. So I've got this set up right now with, they're both 500 millivolts per channel. So my input is 0.5 volts peak minus 0.5, so 1 volt peak to peak. And then what you see is I've got 1.5 on the output and minus 1.5, so I have a gain of 3. Now you can set up cursors. Let's see, Y cursors. Here's one here. Let's see. I think, how do I get my second one? I go up here to Y cursors, I think. Okay, I've got one in, and then I can add another. And then, okay, here's cursor number 2. And then I can reference like that. Oh, and I'll set those on channel 2 as well. And let's see. I thought there was a way where you can display the numbers too. I just added another one, which isn't what I wanted to do. These things are actually a bit clunky for me. I'm used to, oh, come on. I am used to using oscilloscopes where create these different. Okay, what this is saying right now is that what I did is, again, I clicked here and I made the reference for the second cursor. And it says I have 3 volts differential between those two. And then similarly, later in this lab, we'll use the X cursors where you can set those up and those will give you vertical. We'll just address that when we get there. But otherwise, just another quick tour of the analog discovery. To change, let me bring that other screen back out. I'm going to close this for now. Bring the other one out. Okay, so to change the time base, That's very easy. You can come here. I'll put at 500 microseconds per division. Or if we wanted to just look at one waveform, like there's like 100 microseconds and 200. Okay, so you have those kind of controls there for the time base. Set that up as you see fit. Back at 500. And then for the to control the amplitude of the signal, okay, you've got the wave generator, but now if you want to control the amplitude on your display, you can control it here. Like before that was at 500 millivolts per division, and then I switched it. I can switch them both to 200. However, 200 is like off the screen, so I'll go back to 500. Oh, I'll set them both at 1. Okay, but you have that kind of control there to get the signal in the screen. Other details. Let's see, triggering. This one here. Okay, that sets the trigger level. So if your oscilloscope is freewheeling like that, it means you need to bring that trigger level within that level of that signal. And then we can also move the signals apart from each other. So yeah, on the left-hand side, that just controls where the signals are in the display. And on the right-hand side, it controls your trigger levels. And then we can, I think, switch triggering to channel 2. I think that's this button here. Yeah, so I just switched it to channel 2. And then again, if I move out, yeah, it starts freewheeling again. I'm gonna reset to channel 1 and move it back to the middle. But anyway, that's what's going on there. Measurements. We can add define measurements. Okay, so horizontal measurements. Let's see, what do we, there's a menu here. You can do frequency, period, positive width, rise time, fall time, and then vertical. Let's see what that looks like. Okay, so that's the vertical axis. So the horizontal axis was the first one where you can do all the timing type related things. And then here you can do min, max, average, amplitude, and ACRMS, DCRMS, and so forth. So those are them. Okay. I'm just going to close that for now. And then other quickly, let's just go back up here. You do have a voltmeter. I don't have it hooked up right now. And let's see if I say run. Okay, so this is what's going on. Okay, so this is, I had a 1 volt peak. I'm sorry, I had a 500 millivolt peak signal on my input. And so the voltmeter is saying I got 345 millivolts. So 500 times, this is basically an RMS measurement. So 500 times 0.707 is equal to 353. So I'm slightly lower than that. I'm not sure if that's a measurement error or if that's just the where I've got my signal set. And I've just got this kind of DC going on there, and then I've got 2 millivolts at the output, and then I've got 1 volt RMS on my output. So my output was 1.5 peak times 0.707 says I should have 1.06. So it's slightly off. It's 1.043, but close enough for what we're doing. Okay. So anyway, that's the display you're going to get with the non-inverting. Hold on a second. I've got a paper copy of this, of the lab instructions. Let me look at that real quick. Okay. So we're basically start building on step 9. So it says construct the circuit of figure 1. So I showed you a photo of that. And then it says obtain a plot of V in, V out. So we're looking at that right now. And then it says step 1, you 10 plus or minus. I'm sorry, I was reading the wrong instructions. Plus or minus 10 volt power supply. Be sure to use a sensitive. Oh, okay. The first thing they want us to do is measure the offset voltage of the op amp. So even before we kind of got ahead of ourselves, what we're doing right now is essentially step number 11, where we have a 1 kilohertz in and a we have a 1 kilohertz in signal, and we're looking at the input output gain, and we can see our gain is 3. But before we do that, we were supposed to first ground the input on pin 3. So I'm going to do that right now. I'm going to connect a ground. I've got a jumper here on my board, and I'm going to take the signal off, and I'm going to put a ground on the input. And then we're going to see what's going on in the output. Oh, this isn't running. Let me put this on run. Okay, so my input's grounded, and now my output is very low, like we would expect. I'm going to jack up the volts per division and just see what's going on that output in the 10 mil. Okay, so that's what's coming out of the output right now. It's kind of noise. Let's see what the voltmeter is telling us. Okay, I have to run. Apparently I can't run the scope in the, okay, voltmeter at the same time. So I'm going to push run here. And so this is telling me I have 2 millivolts at the output. It does say I have something at the input, and that's probably noise. But again, it's telling me I got a very low voltage at the output. So basically what we did again is on that schematic, I grounded this pin here to the positive input, and we're measuring the voltage here at the output. And on my screen, I'm saying I got 2 millivolts. That's not necessarily my offset voltage, because I do have gain still. I think to get the offset voltage, I would divide that by 3. So in actuality, my offset voltage is 2 divided by 3. So it's like 0.66 millivolts. Okay, so make that measurement, record in your lab report what you did. Also, while you're doing this, take screenshots of the circuit, and take photos of the circuit, post those in report, take screenshots, and record the values where it says to record them. Okay, so I'm going back here to my scope. I'm going to put it on run again, and I'm going to get rid of that ground. See if I can get my signal back. So we just did step number 9, and then getting our signal. I'll set this up again. Put this at 1 volt per division. Oops. Okay, there's my signal again. I'll actually fill the display a little bit more. I put them both at 0.5. Okay, so this display here is essentially step number 11. Now in step 12, it says, make sure the oscilloscope is set for DC coupling. So on the analog discovery, I think it automatically is displayed both AC and DC. And it says, increase the signal amplitude until clipping is obvious. Oh, actually, I want to back up. Okay, I'm sorry. Step 9, we're doing, I'm sorry to jump around like this. Step 9, we measured the offset voltage. Step 10, they wanted us to do a DC sweep. let's skip that because that's just tedious. You can do it if you want. I mean, you just basically put a DC signal in. But what I find is, and it's basically trying to mimic the DC sweep we did in PSpice. But what I find when I'm building these things is best to just put a signal in and just make sure they're working and verify the game. And basically what we're going to do in step 12 is we're going to increase the amplitude until we see where the circuit saturates. So we're basically going to get the same information that we're going to get from the from doing the DC sweep. And so let's just do that right now. I'm going to go to WaveGen. So I've got a plus or minus 5 volt supply. So I've got a potentially dynamic range of plus or minus 10 volts. And I've got a gain of 3. So if I put in 4 volts, it's going to try to go to plus or minus. It's going to try to go to 4 times 3. It's going to try to go to plus 6 and minus 6. So that's going to saturate it. So let's just do that. Let's put on the WaveGen. Let's increase this to, if I go 2 millivolts, let me think. 2 millivolts will give me plus or minus 4. I'm sorry, not 2 millivolts. I want to go to 2 volts. Okay. Now let's see what this looks like on the scope. I'll go to channel 2 and I'll change the scale to 2 volts per division. Okay, so now I see I'm clipping. Now you can go back to measurements and add a, well, let's just do that. Let's just do that. Let's go to measurements and let's see, where was that one I was looking for? Measurements. I want to add vertical. Oh, I just saw it and I forgot how I got there. Okay, just in the interest of time, I'm just going to set these horizontals at the limits. Move this out of the way. So these are the cursors that I set on. And again, you turn on the cursors here, or if you push this Y menu, and they can open up and do it. The one is the reference. And so you set that one first and then you move 2. So this says that I have a delta of 7.86. And then what we see here, we're not going all the way up to plus 5. We're going up to like 4.2 volts in the positive direction. And then here, we can set this cursor up so it'll tell that number too, but let's see if that's easy. Okay, so we went up to 4.2 in the positive direction. And then here in the negative direction, it's trying to go to minus 5 volts, but it can't. So it's only going to minus 6.2. I'm sorry, 3.6. So it's this is that circuitry that I showed you in the internal diagram, that biasing circuitry is preventing us to only go to minus 3.6. Whereas in PSpice, it indicated that we could get to like 0.6 volts from either supply. And in fact, I think there's a question in here somewhere. It says, write a equation for, let me see where that is. I think it's in the conclusion. It says basically write an equation for, maybe it's in the lab, right? It says write an equation for the saturation. And so it's basically, in the positive direction, you can get to VCC minus 0.8 volts. And in the negative direction, you can get to minus VDD, or the minus supply minus, this is 1.4. The minus supply plus, I'm sorry, plus 1.4 volts. So I hope that's not too confusing. But yeah, you basically just say that you can get within this range of the positive supply. And again, the delta here is about 0.8. And this range of the minus supply, which is the delta here, is 1.4 approximately. Okay, so that was step 12. Step 13, I'm going to change this into an inverting amplifier really quick. So I just have to make a few minor changes. I'll take the first resistor that's going to ground, I'll pull it from the ground. And then I'll put the signal there. And then I'll take a ground and I'll plug it in. Okay. Ground, and I'll plug it in into pin 3, which is now floating. And no, I don't have that right. Okay. My signal is going in here. Oh, pin 3 is here. Okay, there's my inverting amplifier. You be patient. My dog gets she gets restless because it's time that we usually go to the DOGGY PARK. Okay, let me go straighten this out again. Let me go back to wave gen. I'm gonna put it at 500. Okay, 500 meg. And my scope, I'll readjust those settings here. 500 and 500. So here's my input. It's plus or minus 1 volt. My output is plus or minus 2 volts. So that is step number 13. So we can verify our gain there. Small signal gain is 2, as it should be. And you see that the signals are 180 degrees out of phase. So the next one, it says, measure the input resistance of Rn. So there's a couple of ways you can do it. You can measure, going back to that diagram. Hold on, let me move this. Probably the most straightforward way is to, oh, where'd that come from? Anyway, the most straightforward way will be to, I didn't call those up. Let me turn those off for now. Remove all. Come on. Oh, okay. Put this over. It's always in the way. Okay, so again, on step 14 right now, we want to measure Rn. Probably the most useful, easiest way to do that. Let's just turn off our signal. We'll go to our voltmeter, which is already at the input. And let's see, ohmmeter. Oh, maybe I'm confused here. Voltmeter, oh, impedance. I just want to measure DC ohms. Let's just run this. Okay, so basically now we have an impedance analyzer, but you could even just use an ohm meter. And then you can put that basically at the input. And if you remember from that diagram of the amplifier, when this node is to ground, this node is to ground. So if you just put an ohm meter here, an impedance analyzer here, you'll measure the impedance of this first resistor. So that's the input resistance or input impedance. Let's see what it says specifically. It says small signal input resistance of the amplifier. So, you know, that resistance would imply DC. But what we're looking at here is even better. We're looking at the impedance. And what we see is it's, yeah, about 1K until we get out to these higher frequencies. And then there's some resonant point that puts a notch in the impedance. That's the kind of stuff that I spent a lot of time just working through and trying to tune those things out of circuits that I design. Is, you know, I design stuff that operates at rather high frequencies, and, you know, a resistor behaves as a resistor, or a capacitor behaves as a capacitor. up to a certain frequency, and then they start getting a little bit nonlinear like this, and you got to find ways to compensate for that or tune it out if you need them to hold a value. Okay, but again, what I just did there, I turned off the wave gen, and then I put on the I went to the menu here, and I basically just turned on the impedance analyzer down here, and it just came up. I mean, that's how easy it is to use this thing. Is it just came up and it shows me. And so what it's showing me is that my input resistance is a little bit more than 1K. Where is it reporting the value? Maybe add trace as a reference. I'll have to dink around with this some more. I haven't used this. So you can do that too. Or yeah, I mean, there's always videos too. I just want to see a basic readout of what it says my resistance is. It's a little bit over 1K, you know, it's saying like, here's 2K here. So it's saying I've got like closer to 1.2K as my input. Okay, but in the interest of time, I'm going to move on. Number 15. Okay, let's go back. We're going to turn wave gen back on. I'm going to turn this one off. And I'm going to turn this one off. And I'm going to put the scope on. I put on run. Okay, so there's my signal. I've got a sine U set going in. And now what we're going to do is we're going to check. 15 is the slew rate, I believe. Yeah, we're going to check the slew rate of the signal. So the slew rate is the rise over the run. There's two kind of characteristics. Like we had this picture here of the bandwidth of the amplifier. This one here. So at unity gain, you'll get something in the order of, on this one, of a mega ohm or a megahertz. And so we've got a gain of 2. So we should be able to get performance out there. But you may not always do that because there's another limitation. And on this, like on this spec sheet here, they have the slew rate, and it says it's expressed as volts per microsecond. And so if your signal is low, you can probably get out to that full unity gain bandwidth or something very high if you have a very low set amplifier set for a low gain. But if you have a large signal and it's trying to push a lot of volts through, it's also limited by the internal circuitry, and it can only put out so many volts per microsecond. In this case here, it says 17 volts per microsecond. Okay, so let's just look at that. The way we test that is we're going to bring the wave, the frequency up to where this output signal starts to distort. And the way it's going to distort is these nice smooth lines. It's not going to be able to keep up this slope here on these signals and so forth. It's not going to be able to get more aggressive and more aggressive. And so these nice clean lines are going to diminish this, especially at the curves, and it's going to turn into a triangle wave. So I'm just going to go into wave gen. Of course, this is in the way. And I'm going to set my frequency. I'm going to set it up. This will go up to megahertz. Let's just try 1 megahertz and see what the signal looks like. Okay, so I got to change my time base. My output attenuated quite a bit. I think I went too high. Let me just, I'm going to back off a little bit because we're pushing into the limits of its operating frequency. I'll try 100 kilohertz first, and let's just see what that looks like. Okay, so now I got to change my time base because I switched. So I'm sorry, time base is here. Let's go to there. Let's bring that out a little bit more if I can. Oh, that was too much. Wrong one. 1 micro. Okay, so I am seeing a little bit of slew. Okay, so you see here, my output is getting distorted, that you can see the hump isn't smooth. And so that's the amplifier trying to, it's got a certain rise over run that it can perform at. It can only push so many volts per microsecond. And so as that frequency goes up, I'll move it one more and we'll see a more pronounced distortion. I'll push it to 200 and then we'll look at the scope. And there you see that it's the signal's even diminishing, and then it's pretty much looks more like a triangle wave than a sinusoid at the output. Okay, I'm going to back that off again just because the signal diminished. So I'm going to go back to 100. Now, just another thing I want to show you though. So is somewhat related to the amplitude of the signal. If I back that amplitude off, so right now it's at 500 millivolts. I'm going to put it at 100 millivolts, and let's just see if it looks more like a sinusoid. See, I backed it off to 100 millivolts, and it's making that nice curve because this slope is more gradual because it's not trying to go so many volts per microsecond. So again, if I come back here now and if I go to like 1 volt per microsecond, again, we see that it's just not keeping up. So that's a limitation of the op amp. And that's this particular one. I mean, you can find op amps that have very, very wide bandwidth. You know, if you're working on RF or, you know, a very high frequency like wireless circuits and so forth. But this one here is more for like audio type signals, stuff below like 100 kilohertz. Okay, so anyway, it says in the lab under 15, sketch the distorted waveform, where we can just take a screenshot. Observe. Okay. The waveform, increase the frequency and amplitude output until some slew rate distortion observed. Sketch the distorted waveform and estimate the slew rate. Okay, so to estimate the slew rate, we'll look at the time difference. So let me move. Can I move these? Oh, come on. Come on. How do I get rid of those? I don't have full view of my screen because I got this silly window here. Let me see if I can turn this on. Remove all. Come on. Okay, there's my vertical cursors. Sorry, it's kind of clunky for me, but I'm used to using different oscilloscopes. Okay, so this says right now, oh, it's expressing millivolts. I want to see the time. The time might be behind this window here at the bottom that I can't see. I want to see the delta time. Come on, give me that window. Oh, it's way behind here. It says, oh gosh, let me move that. Okay. I got so many cursors, I'm confused. Let me remove some of these if I can. Delta, remove. Okay, too many things going on here. Remove. I'm going to remove this one. Okay, this gives me, let's see, 25 microseconds, 30 microseconds. And so I don't know if I trust this delta. It says down here, it says, oh no, 5 microseconds. So I got 5 microseconds between those. And then we can turn on the Y, although I'm not sure if I want to because it's been so clunky. Let me see if I have these cursors still. Okay, I'm afraid to turn it on. Let me go here. Let me remove that. Okay, let me turn on these Ys. Y cursors. Y cursor. Okay, let's put some Y cursors in there. And let me find them. Where are they? I think they're down here. Okay. So let's see what my amplitude is. Okay, that's good enough for now. Okay, so I got 1.5 volts difference over 0.5 milliseconds. So my slew rate is 1.5 divided by 0.5. My slew rate is 3 volts per microsecond. I hope that's not confusing. But anyway, it's this span here and then this amplitude. And I took the delta amplitude and divided by the time. And generally we express slew rate in volts per microsecond. Okay, the next one, I'm gonna just move on in the interest of time. In fact, I'll turn these off because they're kind of in the way. Remove. Move this back down, move this back down. Okay, the next one, it says 15 or 16. We'll set the frequency to 40 kilohertz. This one I don't actually like. This is to test the gain bandwidth of the amplifier. I'll just do it. I don't like the way we do it here. Let's see. Let me put this at 40 kilohertz. There's 50. I think I can dial that in though. Let's see. I think I can just write 40. Okay. Oh, I still have some distortion. I'm going to bring down the amplitude at 500 and see if that's still distorted. Okay, sine wave in, sine wave out. Okay, and I can change my time base back so I see a little bit more. I'll put it at 10. Okay, that's 10 microseconds per division. So now let's see, what does it say here? For the circuit, okay. Oh, we're on step 16 here. Okay, so it says observe the small signal at N2. So that's the summing node. And comment on it as you change the frequency as S12 increases. So I'm going to put the output first on the summing node. So hold on a second. Okay, so that's the output at the summing node. So we have a little bit, and then as we increase the frequency, let's see what happens. First, I'm going to go back to 1 kilohertz because we should see that essentially 0 at 1 kilohertz. Let's see. I got to change my time base. Okay. So that's at 1 kilohertz. I'll put a few more on there. So what I did is I took my output and I put it at the minus input to the op amp. So this is the summing node again. And then as you push the op amp, to its limit. Okay, so right now we have pin 3 tied to ground. So that node should be to ground. But now as we push the frequency up and push it to its limit, that that ground connection there, that voltage at that node will move away from ground. So like at 1 kilohertz, at 10 kilohertz, I think it'll still be good. Oh, we do see a little bit of ripple. So we're kind of pushing in the limits. And then as we get farther up, so I'll put it at 50 kilohertz. And we just see that signal at that where what should be ground start to increase. Okay, so that's basically the point of step 16 is as we push our frequencies up, that summing node, which should be held at a firm ground, it'll start to drift away as we get out of the operating range of the device. And then it says it says be sure slew rate distortion is not present. It looks like we may have a little bit. Calculate the magnitude of the amplifier's open loop gain, and that's V out divided by VN2, which is the summing. So what I'm going to do right now, I'm just going to move the probe that is at the, let me do this, make sure I'm not getting confused here. That's going there, the summing node. I'm going to move the one that's actually at pin 1 now to, oh no, actually I'm going to switch them. I'm going to keep the input now. Yeah, the input here now is the pin at N2. This is going to the output. I'm going to put channel 2 to the output. And then I'm going to put the input at that summing node. And then I'm going to keep the signal where it is. And let's see if I can find channel 2 now. Maybe I messed this up. Channel 2, where are you? Maybe there's a DC offset. Let me do this. I'm gonna go back and just put this down to 1. Scope. I have all this stuff in the way, so it's hard for me to find channel 2. Channel 2, where are you? Come on. Offset. It's got to be down here. I don't see the little caret. Channel 2. Can I drag it? There's a blue line down there. Well, oh, here it is here. Where is it? Okay. So it's just flatlined at the output. Maybe I have that in the wrong spot. We have a little bit of signal on channel 2. Okay. Let's see, I can DC couple. I can't AC couple that. What I want to do is I want to increase the amplitude of channel 2 so that we can see what its amplitude is, and then we can basically make a gain. Let me see what I can do here. Yeah, it goes off screen. Darn it. I'm not sure. I know how to do it with the scopes at the university, but I'm not sure if I'm going to be able to do that here. Yeah, I don't know if I can get a good peak-to-peak measurement off of this guy. I mean, I'm just going to swag it just to move on and get this going. Where's my trigger? Let me see if we can get all these guys triggered. This is always in the way. Yeah, we see just a little bit of movement there. Just to move on and get this going. I'm going to say, okay, this is 4 and 0.5. So that's, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of those little gradical lines is 0.05. So I'm just going to swag it. I'm going to say I've got, here it looks like I've got 3 points. This is 0.5. I'm sorry. It looks like I've got 0.5. I've got like 0.65, 0.7 volts at the at the output. No, I still have that wrong. No, that's what's going on the input. I've got these hooked up wrong. I'm sorry. This goes to, no, I have that right. I'm sorry, I'm confused right now. That's at the summing node. Let me do this. I'm going to bring this up in frequency and let's see if we have something bigger to work with. I'll go back to 50. No, that's not doing it either. Okay, I'm fumbling. I'm not able to make the measurement with this one. I'm a little confused on how to hook it up with, or how to set it up with the analog discovery. You can try it, but basically what you want to look at is what's going on at the summing node, which is my yellow one right now, and then at the output, which is my blue, and that's what's got me confused. I don't have any amplitude at my output, so something's wrong. I don't know. I'm gonna just in the interest of time, I'm gonna hook this back up to where I think it'll be functional. Let's see if I can get back, find my way back. Power. Okay, let me set this up again and see if I got my get back to my differential amplifier. What did I do? There's an offset. Oh, did I? That's maybe what the problem is. Maybe I inadvertently introduced an offset. Where is channel 2 now? I'm lost. It's down here. No offset, no offset. It's down there. Let me go back. I'm gonna change this volts per division. Yeah, my output is flatlined now, so I messed something up. Let me think around with this a little bit more. See if I at least get back to my amplifier. Blue. Power. Input there. Oh, I lost my ground. Oh, okay. That's been my problem. I pulled my ground out, I think. Okay. Okay, let me, no, shush. You're okay. Let me try this one more time. Let me try this one more time. Okay, I'm gonna put the channel 1 at the summing point. And then I'm gonna leave the output and I'm gonna bring the frequency back up to 50K and let's see what happens. Okay, scope. And then let's change the time. Okay. So there's a little bit of slew rate distortion, but just for the interest of time, I'm just gonna take values off of this. I'm just gonna swag them from the screen. So I've got let's see, I've got 100 millivolts per division on the yellow. So it looks like peak to peak. I'm not, rather than put the cursors in, I'm just going to eyeball it. It looks like I've got a little bit of 100. So I've got like 100.2 there and minus 150 there. So I've got 250, 270 volts peak to peak, I'm going to say there. And then on my that was with this scale, the yellow, and then with my blue, it looks like I've got 105 and minus 95. So I basically have 200 millivolts there. So for the gain equation on number 16, I'm going to write that it is 270 millivolts divided by 200 millivolts. And yeah, that's, that's not the best way to, I don't know. I know to measure the gain in a different way. Like I described earlier when I was talking about the gain bandwidth, the way I would measure the gain of the amplifier, the gain characteristic, is I would first set the, first set the gain with the resistors at 1 and measure out which frequency that output starts to diminish. And that's going to be the end frequency in that chart. And then I would change the gain to 10 and then see where it starts to diminish again, and then make a line between those on a graph. And then I could do it again, like with the gain of 100, make another line. And then from that kind of data, I can probably go back and figure out where the corner frequency is. Okay, I'm going to move on to the differential amplifier. So we got 2 more steps. We got a differential amplifier, and then step 18, we hook a circuit to that. So hold on a moment. I'm going to hook the differential amplifier up. Okay. Ground. I'm going to put the signal back at kilohertz. Now my outputs are looking a little funky. That's not right. I gotta fix something still. Let's see. The feedback power. Oh, I gotta get my negative supply. Okay, let's put these on the same scale and see what it looks like. That one at 500. I'll put this one at 500. Okay, so right now I'm driving the negative input to the differential amplifier, the negative side of it, and I've got the positive side grounded. So again, I've got an inverting amplifier like we saw before. I've got a 180-degree phase change. So now I'm gonna, just to demonstrate, I'll switch the input. I'll put the input on the positive one. And I'll ground the negative. And now they're in phase. Looks like it attenuated though. I'm not sure why. Oh, let me lift these up. No, that's not it. I'm not sure why that attenuated. But basically, when you ground the other one, oh, let me, that goes in there. You're okay. You're okay. Shush. I'm gonna put my dog outside. Hold on a second. Come on, you go outside. You go outside. Come on. Okay, let's finish this thing up. So now I've changed that, but my amplitude on my, I'm not sure why, on my positive, when I'm driving the positive input, why I'm seeing some attenuation. They should be the same amplitude. But I've got all the same resistors. It's not clear to me why I'm seeing a different amplitude. Okay, so just in the interest of time and because I'm having apparently some audio problems and a barking dog outside, I'm just going to move on to the next step and show you what it looks like with the common mode. So I'm going to tie both of those together, both inputs together. I'm going to put them both the same node, put my signal in there. This goes here. Okay, so now I'm driving them both. And so the yellow is the input, the blue is the output. And the blue basically looks like it flatlined, but if I jack it up a little bit here, you can see we have, these are in millivolts here. We have about 250 millivolts. I'll put some cursors on that. And I'll put another cursor. Let's see. Cursor, white cursors. Okay. Okay. So it says I've got 400. I've got on the input, I've got yellow. I've got 1 volt peak to peak. And then on the output, I've got 487 millivolts. So my common mode rejection is 48.4 rather, 48.4. Or actually I go 0.0484 divided by 1. So my common mode rejection is 0.048. Not great, but even still though, it's attenuating the signal. Okay, so you want to capture that picture. And then finally, we'll drive that diode circuit that is in step number 18. So let me put those diodes in. Oh, I just had them in my hand. What did I do? Oh, here they are. Hold on a moment while I get these in. Okay, and then one of these goes here, one resistor, and the second resistor goes to the other. And my signal no. There's some in the kitchen. Change this. Okay, let me find my signals. Signal comes in here, the oscilloscope here. Okay, I think I have this working. Now I'm going to bring my signal up so we can see the clamping. Okay, so what you see happening here, this is again, let me move this, move this. Oh, we want to look at the instructions. We've got this signal going in. So we have the differential amplifier connected across plus here, minus here. We got a signal coming in to these devices here. We got the resistor here. And so our waveform at the output, our waveform is plus and minus 2. So it's 4 volts peak to peak, but the diodes are clamping. And so they're only going to plus and minus 1.2 volts. So the forward voltage of the diode is like approximately 0.6 volts. So it'll go 0.6 volts in this direction and 0.6 volts in that direction. And then just for completeness, this is what I'm going to do. I'm going to take, and let me think, what do I want to do? I want to put the oscilloscope probe. I'm going to put the oscilloscope probe like just on reference of one side to ground. So I'm going to put it on the positive side and take, actually, I'll just put it on the negative. So if you just measure on the negative side, oh, that's a little distorted. I don't know if that's going to demonstrate what I want to do. Basically, what I wanted to demonstrate is that it's hard to make that measurement without a differential, the differential amplifier. But anyway, this is the display that you want to get in the last portion of the lab. Okay, I think I'm going to wind this up. Let me look at the questions here real quick. Oh, what step is this? That was a long time ago. I have no idea. You got to speak up. I mean, turn on your microphone and ask me while I'm just talking there and working on things. This last step was 18. You know, when you review the video, just have the instructions out and hopefully you can follow and figure out. Let's see. This is everybody telling where their kits were. Okay, before we sign off, are there any questions that you want to ask? You guys good? Ready to go out and try to build? What you can do too is if you build and you got some wacky waveform, send me an email. In the syllabus, there's my email I look at every day. I don't look at the CSUS emails every day, but if like you're really frustrated and you're just not getting it, you can send it. The email in the syllabus is j.quilici1@sbcglobal.net. And I look at that one, you know, multiple times through the day. And if you send me like a photo of your circuit and a screenshot of what you're seeing on the oscilloscope, I more than likely can help you troubleshoot or send you a message as to what needs to change. So that's one way to I can help you troubleshoot your circuit. But otherwise, work together. You know, you can share what you're getting and your data and so forth. And yeah, hopefully you'll be able to build these basic op-amp circuits. Okay. Any other questions, or I'm about ready to sign out?
Have a good night, boss.
Okay, thank you. Okay, see you guys. See you next week. Next week we're going to do a another op-amp circuit. It's going to be a single supply op-amp, and we'll do Spice first, and then the following week we'll build. Okay, see you guys. Bye.
Have a good weekend.